And taking a second look at the problems. Okay, so the very first part is basically just asking you to draw a plane and intersection. And I'm just going to be super lazy and just like draw the XYZ plane and just kind of draw like XZ plane and the YZ plane, right? So then the point of intersection, the line of intersection is just going to be the Z axis. Yeah. And I'm going to keep using this picture as time goes throughout this discussion, just for something to refer to. But the next part asks for you to find a point that is along the line of intersection. Oh, sorry. I guess you can also just mark any point P on here. Should be pretty straightforward, easy to visualize. And then some vector, I guess, along it would just be parallel to the z-axis, right? So to discuss this, I always never like to give out complete answers, right? I'm trying to get students to understand stuff for themselves. But I think conceptually I can tell you quite a bit. So for the next part, where they give you two specific planes, I won't use those exact planes, but I'll just talk sort of generally. You're asked to find one point which is on the line of intersection, right? And to do that, if you're just given two like arbitrary equations, I'll just choose slightly different ones. I don't know, equals 10 or x plus z is equal to like 2. The idea is when this happens, you can just sort of start by choosing something that they have in common. If they both have x in the equation, you can just sort of choose x is equal to 1 and then try to solve from there, right? And then the next thing I would do is if I choose x to be 1, z at this point would also be 1. And then at this point, if this is 1 and this is 1, then what's left here must be 8. So 2y is equal to 8, or y must be equal to 4. And I think a lot of students might be a little bit uncomfortable with this idea of just starting off by choosing a value. But that concept really isn't that foreign, because I always like to make analogies to one-dimensional calculus, or just a two-dimensional graph. And the idea here is if you had some line like y is equal to x plus x minus 2 or something, and you were asked to find a point on the line, like what you would probably do is just say, okay, I'm going to arbitrarily choose x is equal to 1, and then figure out what y is, right? At this point, y would be equal to -1. So that's pretty much the same idea here. You're just sort of arbitrarily choosing something to start with. You're sort of setting one point down, and that sort of lets you find the other points. Does that make sense?
Yeah, it does.
Yeah. And for this particular problem, just note that, you could have chosen x to be anything. There are certain times, though, where if you had an equation that was just like z is equal to 3, like let's say that was a plane, right? If this was the case, obviously you couldn't set z being equal to 2, right? So that's just one of the rare cases where you're not allowed to select something from the get-go. And the one-dimensional equivalent of that would be if you have just a totally vertical line like x is equal to 2. Obviously, to select some point on the line, you can't just choose some other x value over here, right? So just getting that out of the way. But okay, that's I think the relatively simple stuff. Now we start talking about normal vectors. So if we're asked to find a normal vector for the first plane, we're kind of just asked to find n1, making a right angle to it, and the other problem is sort of asking for n2, making a right angle to that plane. And as a sort of reminder, you can always just sort of look at the equation of the plane and grab the normal vector right from it. So for this plane, with coefficients of 1, 2, and 1, I can tell you right away that the normal vector is 1, 2, 1. It's a really nice shortcut. Do you all remember this? Do you know why this is? Like this right here would be my normal vector. Does this seem familiar, or is this a little bit scary?
It seems familiar, getting the coefficients of the...
Yeah, exactly. Okay, just double checking. As long as it seems familiar, we're good. But if it doesn't seem familiar, go review how the equation of a plane is derived in the first place, and you should be able to figure out why the normal vector components go right into the coefficients. But okay, so that kind of covers 3 and 4, right? If you're given the equation of a plane, you can find the normal vectors. Now, part 5 asks why the vector v must be perpendicular to both these normal vectors. Okay, very good. So on this picture that I have here, just intuitively, you can kind of see this is true, right? if the first plane is sort of the xz axis, xz plane, and the second plane is the yz plane, you can kind of see that the vector we decided was parallel to the line of intersection was basically the z-axis, right? Or the v vector. And you can kind of see that this must be, in fact, perpendicular to both the normal vectors, right? And to think about this a little bit more, it's sort of because the normal vector, let's say n1, is perpendicular to every vector. I'm going to use the word living in the first plane, right? That's kind of the point of a normal vector, is that it's perpendicular to every single vector in that plane. And similarly for n2. For p2, by the way, this word living is just sort of my own creation, or I'm just sort of using it very colloquially. It's not like a rigorous math term, right? This is how I like to explain it. But you can kind of like visualize it, right? For every random vector that you can kind of imagine being in this plane, the point of a normal vector is that it's perpendicular to every single one of these. Yeah? And similarly for n2, it's perpendicular to every single vector living in here. And what can we say about v that is the vector of the intersection of these two planes? Any suggestions? Well, colloquially, I would say that v is living in both p1 and p2. You see that? Do you think that's enough for you to draw your own conclusions? Or should I say a little more?
I think that was sufficient. Thank you.
Okay, very good, very good. Yeah, I guess for anyone listening, right? Just think about this concept of the fact that V has got to be, but by the fact that it's created from the intersection, it's kind of got to be living in or parallel to both planes, and that should tell you about its relationship to both normal vectors. Okay, so I think that was part 5, and part 6 is saying find a vector that is perpendicular to both normal vectors. Well, okay, that's almost kind of the reverse of what we've just done, right? Part 5 was asking us for a vector v that's perpendicular to both, and now they're asking find a vector that is perpendicular to both. Well, that's just exactly what we discussed, right? But maybe they're asking about this in a different way. Maybe they're kind of, depending on how you interpret the question, maybe they're asking for you to construct a vector that's perpendicular to both normals, right? So if we were actually asked to construct something, construct v perpendicular to both n1 and n2, well, think back to your first week or second week of this class. What tool do we have that can take two vectors and spit out a vector perpendicular to them both?
The cross product?
Exactly. Big old cross product. Need I say any more about that?
No, we would just do the cross product for both n1 and n2, right? The normal vectors
You got it.
from questions 3 and 4.
Mm-hmm.
Okay.
And I think we're getting to the end here, but find a vector function for the line of intersection. So at this point, I think we know a point P in the plane, and we know a vector V. So how would we construct a function, the function of a line given a point and a vector? So just sort of drawing this in space, right? We kind of know P, and we kind of know V. How would you turn this into a function? As a reminder, typically this means we want to introduce a parameter. Let's call it t. This isn't meant to be a trick question, but it kind of comes off as one. But just definitionally, if you have a point p, a vector v, and a parameter t, how would you define a line? Right? I'll give you a single variable or 2D example where if I know, if I know the, let's say, intercept, that's b, and I know the slope is m, right? I would say f of x is equal to the slope times x plus b. Yeah? So in the multivariable case, the vector is sort of the multivariable equivalent of a slope. X and t are sort of the parameters, the independent variables. And all that's left is sort of the information about a single point. Where I guess here it's an intercept, here it's a point, but it's kind of the same thing. So just how would you write this in multivariable notation? Let's call it R of t. R of t is equal to what?
The point on the line?
Yeah, just how do you describe a if this describes the entire line in a 2D example, how would you do something similar in 3D? Should I leave it there or should I explicitly answer?
Can you explain it? Yeah, can you?
Sure. So again, I'm trying to kind of draw, like, how do you put it? What I'm a little bit stuck here because it feels like there's almost very little to explain, and saying almost anything would kind of give it away. But basically, we're trying to come up with a function just in the multivariable case, right? And this is what it would look like in the single variable case. If we wanted some function, maybe it would make it easier if I called this t instead of x. But the point is, we have some like point b, except for now it's a multivariable, point in multiple dimensions, so we just call it p instead. And the idea is we start at p, and we want a vector, with some direction, and we want to multiply that by t, an independent variable. You see what I mean? We kind of want to,
So
yeah.
So it'd be RT and then the point, right?
That's the start of. Mhm.
Plus T of the vector multiplied by the vector.
Yeah, exactly. That's all.
Gotcha.
Any other questions, folks? Alrighty, let's call it there.